Training a machine learning model often means choosing numbers, called parameters, so that the model's predictions match data. Gradient descent is the workhorse method for doing that. The whole story fits into one picture, a landscape of loss values and a point sliding downhill until it finds a low spot. Start with the simplest case, one parameter. Imagine a curve where height is the loss and the horizontal axis is the parameter. If you stand at some point, the slope tells you which direction increases the loss. So to decrease loss, you step in the opposite direction. Repeat this, and you slide toward a minimum. The update rule is compact. New parameter equals old parameter minus a learning rate times the derivative of the loss. The derivative is the slope. The learning rate is the step size. Too small and learning crawls. Too large and you can overshoot the minimum and bounce around. Real models have many parameters, so the loss is a surface in high dimensions. We can't draw high dimensions, but two parameters already show the idea. The gradient is a vector pointing uphill, perpendicular to contour lines. Gradient descent moves in the opposite direction, cutting across contours toward lower loss. Now connect this to machine learning. Take linear regression. Predict y from x using a line with slope and intercept. The loss is the average squared error between predictions and data. Gradient descent adjusts slope and intercept to reduce that error, which you can see as the line rotating and shifting to better fit the points. Where do the gradients come from? For each parameter, you ask, if I nudge this parameter a tiny bit, does the loss go up or down, and by how much? Collect all those partial derivatives into one vector, the gradient. In practice, automatic differentiation computes these derivatives exactly and efficiently. There's one more practical twist. Datasets are huge. Computing the gradient using every data point each step can be expensive. Stochastic gradient descent uses a small random batch of data to estimate the gradient. Each step is noisy, but on average it still moves downhill, and it's much faster per update. Put it all together. Define a loss that measures how wrong the model is, compute its gradient with respect to parameters, then repeatedly step opposite the gradient. That's gradient descent. Nearly every modern optimizer is a variation on this theme, adding ideas like momentum and adaptive step sizes, but the core picture remains: follow the slope downhill.